the class. In this particular video, we are going to discuss coordination chemistry, and we are going to take questions which are asked in your June 2019 exam. There were 6-7 questions from this particular topic, so we'll try to cover them up and try to understand that what were the concepts which were asked from this coordination chemistry as such. Okay, so yeah, it's a very important topic. First of all, from inorganic chemistry, this is the one of the topic which covers almost like the maximum weightage from inorganic chemistry, right? Total number of questions which would be asked from here will vary from 6 to 9. So you get around 6 to 9 questions from this topic, and you can easily score around 24 to 30 marks from this particular topic. Okay, so that makes this particular coordination chemistry a very important topic to be covered, right? Difficulty level varies from your moderate to difficult depending upon what kind of question it is asked and the way in which that is asked. That makes the question difficult, although there is not anything which is very difficult from this particular topic. It's just the way of asking, and it's the way how you are understanding the question that will make the question moderate or difficult, right? So having said that, let's start with the first question over here. It was asked in your June 2019 for 2 marks, and it says that the self-exchange electron transfer is fastest in. Now you have 4 different options, and you have to tell that where this self-exchange electron transfer is fastest. Now see, whenever this question is asked from self-exchange reaction or self-exchange electron transfer reaction, what you have to see is the difference in bond length. Okay, the difference in bond length of what? Of whose bond length? So the bond length of oxidant means the one which is getting oxidized, and reductant. Okay, so the difference in bond length of oxidant and reductant should be minimum, or it should not be that much. Okay, so that is something which you have to keep in mind. Now here, if you look upon the options, one more thing before understanding this bond length, you should know that if Eg orbitals are involved, are involved in bond formation, then what happens, or basically in the complex, then what happens that the bond length increases. Okay, in that case the bond length increases. Now if you look upon the options over here, in the first one you have ruthenium in +2 state and you have ruthenium in +3 state. In both the cases, if the ruthenium is in +2 state, it's the hybridization, the electronic configuration will be T2G6, right? Because it will form a high spin complex. So it will be T2G6 and Eg0. Whereas ruthenium +3 will have T2G5 and Eg0. Okay, so this will be the electronic configuration. Now if you see, the Eg orbitals are not involved over here in the bond formation, or there is no electron in the Eg orbital, so Eg orbital is not involved in the bond formation basically. So what will happen, that the bond length of this oxidant and the reductant both will be same. Okay, so the bond length of both of them will be quite similar, and that's why the activation energy of the reaction will be smaller, and thus the reaction will be fast. So the first option comes out to be correct one. If you want, you can check for the other one as well. If you go for cobalt, so cobalt is in +2 state and cobalt is in +3 state. Okay, so if you have cobalt in +2 state, this is this will be with NH3, this in +2 state, it will form a high spin complex, right? So high spin complex, how you will draw? So high spin complex will be something like this. So 1, 2, 3, 4, 5, D7, right? 6 and 7. Now you can see electrons are there in the Eg orbital. So the bond length will be different over here. Whereas cobalt +3 with NH3 will form a low spin complex and will be D6. So the electronic configuration will be something like this, that you will be having 6 electrons over here. Okay, so Eg orbital is not involved. So the bond length of cobalt +3 will be smaller, whereas for cobalt +2 it will be longer. Okay, so that's why the activation energy will be higher. You can check for the other as well. Just you have to draw the electronic configuration, and then you will see that in other options, that is in option number 3 and 4 both, you will be having involvement of your Eg orbitals. Okay, if the Eg orbitals are involved, in that case bond length will increase, thus making the activation energy higher and the reaction slower. Okay, so remember this thing, that if the difference in bond length of oxidant and reductant is small, then in that particular case the activation energy will also be small, and if the activation energy is small, then the reaction will be fast. And when the bond length will increase or decrease, that depends upon the Eg orbital, that whether where your electron are. If the electrons are there in Eg orbital, in that case bond length will increase. Okay, that's the whole concept about this question. I hope you guys got it. So option number 1 is the correct option for this particular question. Let's go to the next question now. Alright, so this was again asked for 4 marks in your June 2019 exam. It says that the correct set of information is, you are given with 4 different points and you have to tell which information is correct. So basically if you look, they are talking about manganese in +2 oxidation state with water as a complex. So I'll just draw over here. So manganese is in +2 state, and since water over here is a weak field ligand which will be behaving as a weak field ligand, so it will form a high spin complex, right? So a high spin complex. Manganese +2, if I draw the splitting, it's octahedral complex. So if I draw the splitting of orbital, so this is going to be a d5 complex. All right. So d5, when you have d5 orbital, in that particular case, there is no involvement of your like orbital concept. Okay, so that or the orbital coupling will not be observed. So remember, orbital coupling is absent in this case. So if orbital coupling is absent, then what happens? That the mu observed, that means observed magnetic moment, will be equal to mu spin. That means it will be just equal to the spin only magnetic moment. Now the question arises that when this orbital coupling will be present. Okay, so remember, if, okay, I'm just writing over here that if your T2G orbitals, okay, T2G orbitals are filled, okay, or I should write that if only T2G orbitals are filled and there is no electron in the Ag orbitals, in that particular case we say that, or you can say that if T2G orbitals are asymmetrically filled, okay, are asymmetrically filled. If T2G orbitals are asymmetrically filled, in that particular case we say that there will be orbital contribution, and if the orbital contribution comes, in that case your mu observed, that means observed magnetic moment, will be more than your spin magnetic moment. Since over here your T2G orbital and Eg orbital both are symmetrically filled, so there is no orbital coupling over here, and that's why mu observed and mu spin will be both equal. So magnetic moment will be same. That means you can easily cancel out option number 2, right? You can either, now you have choice between 1, 3 and 4. Talking about the other one, here you have been given with cobalt H2O whole 6, and this is in +3 state. So remember, when the cobalt is in +3 state, and if it is like when the cobalt is in +3 state and if it is present with nitrogen donor ligands or oxygen donor ligands, so these two ligands are important. Okay, oxygen donor ligand or nitrogen donor ligand, if that is present in the particular molecule, in that case your complex becomes low spin complex. Okay, remember, cobalt in +3 state with oxygen donor and nitrogen donor ligands is a low spin complex. So if I just draw it again, it's an octahedral species, so I'll just split it up. So this is what I'll get, because cobalt in +3 is a D6 molecule, right? So if it is so it becomes diamagnetic. Okay, diamagnetic. What is paramagnetic? So if you have any unpaired electron, that makes the molecule paramagnetic. But since all the electrons are paired, so that's why it will be diamagnetic. So which is the correct option then? So it's a diamagnetic, and also your mu observed is equals to mu spin. So correct option comes out to be option number 3. That's how you can easily do this question. Okay, you just need to know two concepts. The concept of orbital splitting, orbital coupling, when it will be applied and when not. And the other one is that cobalt in +3 state with oxygen and nitrogen donor ligands behave as a low spin complex, and in that case it will become diamagnetic molecule, right? Okay, let's go to the next question then. Alright, so in this particular question it says that consider the following statement regarding electronic spectra of high spin complexes, and these are the 4 statements given. The first one says titanium +3 complex exhibit 1 sharp band. Second statement says that cobalt +2 and chromium +3 complex exhibit 2 broad band. Third one says that manganese in +2 complex exhibit a series of weak and sharp bands. Alright, the fourth one says nickel in +2 complexes exhibit 3 broad band. Okay, you have to tell that which are the correct statement. Now this question was again asked for 4 marks in your CSIR June 2019 exam. We have to deal with each and every statement one by one. Okay, so talking about the first statement over here, the first statement says that titanium in +3 complex exhibit 1 sharp band. Now titanium in +3, what it will be? So titanium in +3 will be actually your D1 species, right? D1, and it is octahedral in species. So what you have to look is you have to go for the Orgel diagram of that. Okay, so D1 in octahedral has a Orgel diagram something like this. This is T1G, this is T2G. Okay, so this is T2G and this is Eg. So the transition will be from T2G to Eg. So there is just one transition which is possible, but this transition will be sharp or broad that depends upon whether there is distortion or not. So D1 is going to give you weak John-Taylor distortion, right? There will be John-Taylor distortion. John-Taylor distortion. So due to this John-Taylor distortion, what is going to happen, that this particular this band is going to become broad. Okay, so titanium in +3 state gives you broad band, not a sharp band. Okay, so it should be broad band basically. So broad band. So that means first statement is not correct. Talking about the second one, where it says cobalt and chromium +3. So cobalt in +3, cobalt in +2, and chromium in +3. So cobalt in +2 is actually your D7, right? And chromium in +3 is actually your D3. So these are the two electronic configuration of them. Now if you look upon the Orgel diagram related to these two, so the Orgel diagram is something like this. You have T1G as the lowest one, then comes your T2G, then comes your A2G, and you also have one that is called as T1GF. Now if you look upon the number of transitions, so this is the first band which you will get from T1G to T2G, the second one you will get from T1G to A2G, and the third one you will get from T1G to T1GF. So the second statement which says cobalt +2 and chromium +3 complex exhibit 2 broad band. So that is also wrong. Okay, that means it gives 3 bands, not 2 broad bands. Okay, so it gives 3 broad bands. So second statement is also wrong. Going for the third one, it says manganese +2 complex exhibits series of weak and sharp bands. Now if you look upon this, so I'll do it over here. So manganese in +2 state, that means it's a D5 complex. D5 complex means your EG and T2G orbital both are actually filled, right? Both of them are filled. Now obviously there will be, if you want to do the transition, the first transition which will be done will be spin forbidden, because you have to change the spin, right? So that transition will be spin forbidden because of the like change in the spin. So that is going to be a weak band. Okay, again if you want to do one more transition, that is again going to be weak band. So there will be a lot of weak and sharp bands in this particular transitions are there. But since the molecule will show like 5 unpaired electron are present, so that's why the transition, there will be spin change in the spin, and that's why some transition will be spin allowed, some will be spin forbidden. So that's why you'll get a series of weak and sharp bands. So third statement is correct statement about manganese in +2. Talking about the last one, where it says that nickel in +2 exhibit 3 broad bands. So nickel in +2, if I talk about nickel in +2 state, so this is actually a D8 species, right? D8 octahedral species. Again you have to draw the Orgel diagram of this. So Orgel diagram will be something like this. Okay, so here it's 3F. Okay, remember this, and this one is 3P. Okay, so just remember that. All right, so here what it will be, yeah, so if you just draw that, so here it will be A1G, then comes your T2G, then comes your T1G, right? And then this will be following the non-crossover rule, it will be T1GF. So this is how the Orgel diagram will be, and how many transitions are possible. So the first transition will be from here to here, the second transition from here to here, and the third one from A2G to T1GF. So actually you are getting 3 peaks, okay, 3 bands, and these 3 bands will be broad band because it's a D8 species, right? And it's a D8 species, and also there is a non-crossover rule which is being followed. Because of both of these things, the peaks or the bands will become broad band, and also the energy difference between these two is very small, so that's why they will become a broad band. Okay, so option number D is also correct. So which will be the correct answer for this question? So option number 3 is going to be the correct option, where C and D both statements are correct. A and B are the wrong statements for this particular question. All right, I hope you guys understood it. Okay, let's take the next question then. Alright, so this question, it was asked that hydrolysis of trans COL whole twice. Okay, so it's a complex given to you, and where L can be any of these ligands like NO2, NCS, OH, Cl. Result in product A, the tendency to form cis-isomer of product A follows the order. So which of these will follow the order of formation of cis-isomer, right? So that's what we have to tell. So to answer this particular question, there are 2 ways. First one is you can easily go with the trans series. Okay, just you can just follow the trans series, and that is going to give you the answer. Now I'll just explain it. Okay, I'll just try to explain it a little bit. So this particular complex where you have cobalt and you have, let's say, you have an octahedral complex, right? So N of ethylene diamine, and then you have, let's say, okay, N and N on of ethylene diamine. This is L, and this is some chlorine. Okay, so in the first step, your chlorine will be gone, and you will be having activated. Basically, you will be having an intermediate. Okay, so N and ligand will be. Okay, so these are joined actually with each other. So this is what it will be formed. And here, if you look, so in this case, your water can react. Okay, H2O can react. Okay, so that's what it is. So hydrolysis, because it's given, right, that the hydrolysis of the trans-isomer. So in this particular step, you can see that the hydrolysis can be done in two forms. Either it can react from this side, or this water can come and it can bind from the above side. If it comes from this particular side, from this side, so basically you will be forming a trans-isomer. Okay, where you will be having CO, and your N and N were like that only, and this N and this N is as it is. You have this L, and over here you will be having H2. So this is called as the trans product. Okay, this will be the trans product. Or if it attacks from this particular side, then the cis product will be formed, and in that case you can say it in this way, that you have cobalt, and let's say, okay, so let's say you have something like this. Okay, so you have N and N, so they will be cis to each other. That's why it will be called as cis-isomer. So here it will be H2O and L. I'll put L at the same position. So L and H2. So this is your cis-isomer. Okay, this is cis-isomer. Now you can see that the stereochemical consequence of the substitution, what happened just now on the octahedral complex, are much more in like see, in the square planar, if you see, the stereochemical consequences of substitution is less. Okay, in the octahedral complex, that is more, because one of the ligand is leaving the site, and in the next case one of the ligand is coming at its site. Okay, so that means it can come from the two ways. That's what is explained over here. The cis complex do not undergo isomerization over here when the substitution occurs, whereas the trans isomers show the tendency to isomerize in the order. So what is the order of trans isomer to in which the trans isomer isomerizes? That depends upon the trans effect. And if you look upon the trans effect, so the series goes in this way, that is NO2 minus is the smallest in that, then comes your chlorine, and then okay, so this is okay. So basically, if you look upon the trans series, if you just look upon the trans series, you will find that your NO2 is highest in that. That means the tendency to tendency of removal of the ligand present trans to it is highest if NO2 is present in that case. Then you have chloride over here, let's say, and then you have NCS minus, and then you have OH minus. So this is the series of the trans. This comes from the trans series. Okay, what is trans series? Trans series tells you that, okay, if you have a ligand and if another ligand is present trans to it, so this particular ligand, the one which is given in the series, it has a tendency to make that trans ligand go out of the reaction, okay, or just leave the reactive site. So that's what it means. So here it says that the hydrolysis of this molecule you are doing result in product A. Okay, you are forming product A. The tendency to form cis-isomer of the product A follows the order. So what you can say, the tendency to form trans-isomer is this. Okay, this is the tendency to form the trans-isomer. If you want to find out the tendency to form cis-isomer, that will be reverse of the trans order, right? So if this is the tendency, this order is called as trans series. Okay, you can search it out for trans series in any of the standard books, you will find it. So trans series is this, but in the question it is asked the tendency to form cis-isomer. So if some molecule is allowing its trans ligand to leave the site, so obviously the product which will be formed will be trans product, right? But we want cis product in this particular case. So in order to form cis product, we have to reverse the series. That's all you have to do. So if you just reverse this series, we will find out that NO2 minus will be smallest, then comes your chloride, then comes your NCS minus, and the last one will be OH minus. If you just match it up with any of the option, you will find out that option number 2 is the correct option. Now this is the tendency. This tells you the tendency to form cis-isomer. Okay, this is the tendency to form cis-isomer, this particular series. So that's how you can easily answer it. Okay, The steps which I have shown is just the mechanism that how the reaction will happen actually. Alright, so let's talk about this question over here. Now it says that an aqueous solution of metal ion A gives blood red colored product B, okay, upon reaction with KSCN. Now upon drop-wise addition of NaF, the complex turns to a colorless compound, that is C. Identify A, B and C. So that's what it is said. Now you have compound A already given to you, that is aqueous solution of metal ion, okay, and it gives you blood red colored compound B, and okay, fine. So let's take that the metal in the starting, let's say that the metal is in +2 state, okay. If Fe is in +2 state, FeH2O6, this will be the aqueous solution of iron in +2 state. No, this will be actually a D6 high spin, right? D6 high spin state, and if you look upon this, it will have electronic configuration of like this, right? Now it will show DD transition, and that's why it will not be a colorless compound. So aqueous solution of metal A gives blood red colored with compound B, and upon reaction with KSCN. So if you react it with KSCN, you are not going to get a blood red compound, okay, because if you react with KSCN, what you are going to get is FeH2O5 and SCN, and it will be what? It will be in +1, because overall state should be +2. So that's how it will be. It will not be blood red color because iron is in lower oxidation state over here. Iron is in +2 oxidation state. Okay, so there will be no ligand to metal charge transfer, and if there is no ligand to metal charge transfer, so this is not going to show intense color. So that means in the starting which we have taken, that is we have taken iron to be in +2 state, that is wrong. We have to start from iron in +3 state, okay. So we have started, let's say, with iron aqueous complex of iron in +3 state. Now it becomes a D6 high spin complex, right? And D6 high spin, if you draw the electronic configuration, so it will be something like this. Now it will not show any DD transition, alright. Now this is aqueous solution. If you react with it with KSCN, what you are going to get is FeH2O5 and SCN, okay, and along with that you will get oxidation state of +2. So overall iron will be in +3 oxidation state. That's what it will be. Okay, so that means now you will get LMCT, that is ligand to metal charge transfer. Your ligand over here is a good pi donor ligand, and metal is in high oxidation state, that is in +3 oxidation state. Iron over here is in +3 state. So that's why ligand to metal charge transfer is possible over here, and since ligand to metal charge transfer is possible, so the color of the compound will be intense, and that's why it is given that it is blood red in color. So the color is blood red. Now in the next, what they are doing is they are adding dropwise NaF, okay. So they are now adding NaF to it. So if you add that, what it will do, now slowly if you are adding this NaF, so fluoride ion is going to replace all these ligands from this iron. So what complex we are going to get is FeF6 and 3-. So iron is in +3 oxidation state here as well, but the ligands are changed to fluoride. So here if you look, it again came out to D6 and high spin complex, and now again there is no LMCT, nothing possible over here because ligand is not a pi donor ligand over here. So what is possible now is DD transition, okay. So DD transition is possible, and this DD transition will be spin forbidden, right? Because spin forbidden, Laporte forbidden, all these like the transitions will be spin and Laporte forbidden. Okay, so if it is Laporte and spin forbidden, that's why the color of the transition will be not possible. Okay, so the color you will get for the transition or the band will be colorless. Okay, so that's why the compound C comes out to be colorless compound. Alright, so that's how we have identified our compound A, B, and C. So our compound A is nothing but iron in +3 oxidation state. Compound B is FeH2O5 SCN 2+, and your compound C is nothing but FeF6 3-. So if you look upon the options, your option number 2 comes out to be the correct option for this particular question. Alright, so that's what about this particular question is. Alright, so let's talk about this last question over here. It says that considering S bonding only in the molecular orbital diagram of metal complex with the trigonal bipyramidal geometry, the d orbital which remain non-bonding is, okay, so which d orbital does not participate in bonding, that's what they are asking. Now if you look upon the splitting of d orbital for your trigonal bipyramidal geometry, you will find out that your d orbital actually splits in this way, that is, okay, I'll just write down the splitting. So this is your dxz and dyz. This is your dxy and dx square y square, and this is dz square. So this is how your orbitals will split. Okay. Now over here, the above two are actually behaving as anti-bonding orbitals. Okay. So they will be anti-bonding orbitals, and this particular one will be non-bonding orbital. So non-bonding orbital does not participate in bonding. Anti-bonding orbital has a non like anti-bonding character. Bonding orbital participate in bonding, but non-bonding orbital neither they behave as bonding orbital, neither they behave as anti-bonding orbital. So the non-bonding orbitals which will remain over here will be your dxz and dyz. So for this, to answer this question, it was very simple. Option number 2 is the correct option. In order to answer this question, you just need to know the splitting pattern of your d orbital. That's all. And the molecular orbital theory. In the molecular orbital theory, if you look, you will find out that when the d orbital splits, your higher d orbitals behave as anti-bonding d orbital, whereas the lower one behave as the non-bonding. Okay, so that's why this particular one will behave as the non-bonding orbital. So that's all, and that's how these questions has to be done. I hope whatever questions I have taught, whatever questions I have taken in the class, I hope these all were clear to you. You guys understood it well, that which concepts are there and how I have applied them. And in future, if similar questions will be asked, you guys will be confident enough to answer them. All right. So I'll just summarize up everything now. So the level of questions which were there in the video over here, the questions which we have taken 6 questions. Out of them, if I want to tell, so they were like quite difficult questions only. Okay, so out of 6, I would say that 4 were difficult. Okay, 4 were difficult question and 2 were easy. Now which 2 were easy? Let me just get back to the questions. So this was an easy question. Okay, it was an easy question. If you go back to this particular one, this was a little difficult question. You need to know a lot of things over here. Okay, so this was a little difficult one, I would say. This one, you just need to know the trans series and you just have to reverse that. So I would say this is an easy question. Okay, coming to this particular question, this is also a little tricky one. You need to know about manganese in +2 state, then only you could do this question. So this is also, I would say, a difficult one. Coming to the other one, this one was also a little difficult based upon this thing, whether you know or not, that cobalt in +3 state with oxygen donor ligand, it behaves as a low spin complex. If you know this, this was easy, otherwise it was difficult. So it's, I would say it's a moderate one. Okay, so this is moderate question. And the first one, it was very easy. Okay, or if you just know the concept of the EG orbital and how it is involved in the bonding, so I would say this is also moderate. So if I have to summarize it properly, so I would say that out of this, 2 were difficult, 2 were easy, and 2 were moderate question. Okay, so this is how the questions were. The concepts which were used in this in the videos, in the video which I have taken, the concepts which are used, first was inert and labile complexes. Inert and labile complexes. Then the concept of Orgel diagram was used. Okay, Orgel diagram was used. Then the concept of your magnetic moment was used. Magnetic moment. Then there was a concept of your trans series. Okay, trans series. And the last one was on the charge transfer spectra. Charge transfer spectra. So if you know these things, and one more, that was d orbital splitting, right? D orbital splitting. D orbital splitting, or I would say a molecular orbital diagram of that. Molecular orbital theory related to that. So these were the concepts which are used in the question to solve. And the useful tip which I would give you is follow standard books to study this. Okay, follow standard books in order to cover these concepts and try to practice questions related to this. This is going to help you a lot. Okay, so practice questions related to the topics which I have covered in the video. Okay, so that's all from my side, guys. Thank you so much for watching, and that's all for this video. I'll see you guys in the next video with new concept, with new questions. Till then, have a great day.